We just finished talking about the first type of facilitated diffusion, which was channel-mediated facilitated diffusion. This was used for small polar molecules to be able to pass through the membrane and be shielded from the nonpolar interior of the cell through the use of a channel protein. The other type of facilitated diffusion would be carrier-mediated. A carrier-mediated diffusion involves a transport protein, but instead of a channel like we saw here, we see a protein that actually changes shape to allow a large molecule to be sent from one side to the other. If you use this as an example, this was really simplifying it, but let's say that we have a molecule that binds on the outside of this carrier protein. Well, when it binds, this carrier protein changes shape and it releases that molecule onto the inside of the cell. This can happen in the opposite way, obviously, as well. But carrier-mediated diffusion involves a shape change or a conformational change in the protein that releases a molecule from one side to the other. So channel proteins are typically used for small polar molecules, and carrier proteins are typically used for large molecules or large polar molecules. The important part about this is that in facilitated diffusion, we are still going to be going down a concentration gradient. Because this is passive transport, we are still going down the gradient. No ATP is needed, and molecules go from an area of high concentration on one side to an area of low concentration to the other side. That means that this process can happen in either direction. It can start outside the cell and move to the inside, but then once the high concentration gets on the inside of the cell, this can go from the inside to the outside. It all goes down the concentration gradient, and it all happens in kind of a random motion activity based on that bouncing and kinetic energy that we talked about for these molecules. So in facilitated diffusion, these channel proteins or these carrier proteins don't go out and actively grab anything. There is usually just some type of an attraction from that molecule to the protein that allows for the transfer to happen, but it still always happens based on the concentration gradient, and it goes down the concentration gradient. Now, another issue with passive transport has to do with the movement of water itself. Remember that we said we really defined diffusion as the movement of solute particles, which were dissolved in water. We can also actually talk about the movement of water down its concentration gradient. Water is going to behave really in a similar way as to the solute particles that we just talked about. Water will also go down its concentration gradient. It will cross a membrane and go down its gradient. Water will go from an area of high water concentration to an area of low water concentration. You can see here that there is high water, and here there is low water concentration. So water is going to move in this general direction to the right until equilibrium, remember, equilibrium is the goal for passive transport. So equilibrium is going to be reached where we have an equal amount of water on the left and the right. Now, another thing to think about when we're dealing with osmosis, you can see in this example. So there are some red solute particles mixed in with this water, right? In the side of this diagram that displays high water, we also can say that we have low solute, because the water displaces the solute and vice versa. On this side where we have low water, we have filled up that space with high solute. So these are always going to be in opposition. Where you have a high water concentration on one side, you will automatically have a low solute in comparison to the other side. A low water concentration will always be joined with a high solute concentration. Otherwise, it would be equilibrium, and you would have equal amounts of water and solute on both sides. Let me erase this for you real quick, and I want to show you another way to think about osmosis. Osmosis is also going to be the movement of water towards high solute. If you think about this, water is always going to attempt to dilute a high solute area. Again, with the goal of reaching equilibrium. Okay? Now, solute particles can't always cross a membrane. It really depends on the type of protein channels or carriers that are present, or it depends on if these molecules are able to utilize simple diffusion and pass through the membrane anytime they want to. But a lot of times these solute particles can't pass through anytime they want to, and water is always the molecule that can move through our membrane. It can move through any time it wants, and it really is going to always move based on this idea of high solute. So what happens is that water, while yes, it goes towards low solute, it goes from high water, let me say that again. Water goes from high water concentration to low water concentration, but water also goes towards the high solute in an attempt to dilute the high solute area and bring us to equilibrium. Let me erase this again and make sure that you see what I'm talking about. Water, sorry, that's my dog in the background. He wants to play. Water is always going to try to dilute the high solute. And if that solute can't move, and water is the only thing that moves, it's going to go ahead and do that. So let's move ahead to the next figure. This is a diagram that shows a pretend membrane. Let's pretend like this is our cell membrane, and these are solute molecules. In this example, these are sugars. These sugar molecules are not able to pass through the membrane. So this membrane is selectively permeable, and the sugar cannot cross. So if this was an example of our cell, it might be that there are no transport proteins that will allow this sugar to pass through. So the sugar is stuck on side B in this example. But remember, we said that water can always move through whenever it wants to, how often, how much. Water can always move. Now, where is the high solute in this example? Well, the high solute is over here. That's where the sugar is. And because water always moves towards the high solute, you can see that the water moves into side B. And because all of the solute is stuck on side B and nothing comes over, you actually see a drop in the volume of side A as the water utilizes osmosis to travel over to side B and dilute the solute. All right? So water always goes from high water concentration to low water concentration. Or you can say that water goes from one side towards the high solute. So water undergoes osmosis to move towards the high solute concentration. Now, this actually can have really big implications in our body cells. So I want to talk a little bit more about osmosis as it relates to our body cells. And our blood cells are a really good example of this scenario. There are three terms that we need to define here: hypotonic solution, isotonic solution, and hypertonic solution. All of these terms are in relation to solute concentration. Okay, these three terms I want you to remember are in relation to solute concentration. Okay, let's talk about these really quick. One, hypotonic. Hypo means low. Like hypodermis is the lowest part of your skin. So hypo means low. A hypotonic solution has a lower solute than in the cell. The opposite would be a hypertonic solution. If somebody is really hyper and bouncy, well, they are pumped up. So we would say that that would be a high solute. So a hypertonic solution has a higher solute than in the cell. And then thirdly is our state of equilibrium, and this is called iso. Iso means the same. And isotonic means equal solute to what's found in the cell. So all three of these solutions are talking about what the cell is being surrounded by, or what the cell is suspended in. So let me erase these really quick, and let's go through this example again. Actually, I'm not going to erase everything. I'm just going to erase parts of this so we can talk about it a little bit more. I'll leave my definitions up there. All right, so let's go through these one more time. Here we go. So if we start with an isotonic solution, remember isotonic means equal. So we have equal amounts of solute inside and equal amounts of solute outside. That means that water moves in and out at the exact same rate. So there is no volume change. Does that make sense? Because there's an equal amount of solute inside and outside of the cell, the movement of water in and out of the cell through osmosis is going to be equal in both directions. So water moves out just as often as water moves in, and there's no volume change in that cell. Let me erase that again, because everything's getting a little busy. All right. Now, isotonic was the easy one because everything is the same and nothing changes. But let's move over here to hypertonic. Remember hyper, woohoo, hyper is high, bouncy. Hypertonic has a high solute compared to what's in the cell. So the high solute is outside of the cell. We said that water always moves to high solute. So if you let that be your rule, every time we're talking about osmosis, water always moves to high solute. If we've said that the high solute is outside of the cell, then water is going to move out towards that high solute to try to dilute the solution. But when that happens, the cell loses water and shrinks. Okay, so you can see the risk of putting a cell into a very hypertonic solution would be that the cell would lose water and shrink. All right, this is a process called crenation or crenate, when the cell shrinks and shrivels up. Okay, now the opposite will also be true. If we put a cell in a hypotonic solution, that means that there is a low solute out here. If there's a low solute out here, then you automatically know that there is a high solute in comparison inside the cell. Rule still applies. Water goes towards high solute, so water moves into the cell, and that cell is going to swell and get bigger and rupture, and that is called lysis, when the cell ruptures because it gets so full of fluid.